Welcome to all. Today we are going to see about basis and related theorems. Let us see the definition of basis. A linearly independent subset S of a vector space V which spans the whole space V is called a basis of the vector space. That is, basis means two conditions satisfied. One is linearly independent and another one is L of S equal to V. Linearly independent subset S of V and L of S equal to V is called the basis of the vector space. Let us see the example. Let S equal to set of vectors 1 0 0 0 1 0 1 1 1 is a basis for V3 of R. Let us see the proof of the example. We shall show that any element A, B, C of B3 of R can be uniquely expressed as a linear combination of the vectors of S. That is, the linear combination of the vectors S. That is, let S equal A, B, C equal to alpha into the linear combination of the term 1 0 0 plus beta into 0 1 0 plus gamma into 1 1 1. It is, we put it them, it is equation 1. Therefore, ABC equal to multiplying the scalars and adding that term, we simplify that, we get alpha plus gamma, comma, beta plus gamma, comma, gamma, comparing that term left and right side. Therefore, alpha plus gamma equal to A and beta plus gamma equal to B, then gamma equal to C. Substitute them gamma equal to C in these two terms. Hence, we get alpha equal to A minus C and beta equal to B minus C. From 1, we substitute that value alpha and beta. Therefore, A comma B comma C equal to alpha is A minus C into 1 0 0 plus beta is B minus C into 0 1 0 plus gamma is C is comma into 1 1 1. It is the linear combination of that term by that vector ABC. ABC means V3 of R. V3 of R equal to the linear combination of the term. Therefore, S is a basis of V3 of R. Let us see the another example. Let S equal to set of vector 1 0 0 and 1 1 0 is linearly independent but not a basis of V3 of R. It is linearly independent but it is not a basis. Let us see the proof of the example. Let alpha into 1 0 0 plus beta into 1 1 0 equal to the 0 0 0 vector. It is the linear combination of the form. Multiplying the scalars and adding that term, we simplify that, comparing that terms alpha plus beta equal to 0 and beta equal to 0. Beta equal to 0, substitute them in this equation. Therefore, alpha equal to 0. So, therefore, we get alpha equal to beta equal to 0. The scalar value is equal to 0. Hence, S is linearly independent. Also, L of S equal to the linear combination of the term. That term, we get the result A, B, comma 0, such that A, comma B belongs to R. It is not equal to V3 of R. L of S not equal to V3 of R. Hence, it is not a basis. It is a linearly independent set, but it is not a basis. Let us see the theorem. Any finite dimensional vector space V contain a finite number of linearly independent vectors. It spans V. That is, linearly independent set and spans V is called a basis. That is, a finite dimensional vector space has a basis consisting of a finite number of vectors. Let us see the proof of the theorem. Let V is a finite dimensional. There exists a finite subset S of V such that L of S equal to V. Here it is a span. Span means L of S equal to V. We know that V be a vector space over F, S equal to set of vectors n vectors v1 to vn and L of s equal to w, we get the result there exists a linearly independent subset s dash of s such that L of s dash equal to w. Using this result, this set S contain the linearly independent subset. S contain linearly independent subset and S dash equal to v1 to vn vector such that L of S dash equal to L of S equal to v. Therefore, L of S dash equal to v, hence S dash is linearly independent and L of S dash equal to v, hence S dash is a basis for v. Hence the result. Next we see the another theorem. Let V be a vector space over a field F, then S equal to V1, V2, etc. Vn is a basis. Basis means linearly independent and L of S equal to V. If and only if every element of V can be uniquely expressed as the linear combination of the element of S. It is uniquely expressed as the linear combination of the element of S. Let us see the proof of the theorem. Let S be a basis for V. Basis means that by the definition of basis, S is linearly independent and L of S equal to V. So, every element of V can be uniquely expressed as the linear combination of the element of S. Hence, the first part is over. Next, conversely, suppose every element of V can be uniquely expressed as the linear combination of the element of S. We have to show that S is a basis. Clearly, that form is L of S equal to V. Next, we take alpha 1 V1 plus alpha 2 V2 plus alpha n Vn equal to 0. Here, V1 to Vn is a linear span. So, that condition alpha 1 V1 plus alpha 2 V2 plus alpha n Vn equal to 0. Also, 0 V1 plus 0 V2 plus 0 Vn equal to 0. Thus, we have expressed 0 vector as the combination of the S in two ways. Comparing that, therefore, alpha 1 equal to 0 and alpha 2 equal to 0, alpha n equal to 0. By hypothesis, this linear combination of the term and the scalar's values, all values are 0. So, S is linearly independent. L of S equal to V and S is linearly independent. Hence, S is a basis. Hence, the result. Next, we see the another theorem. Let B be a vector space over a field F. Let S1 equal to set of vectors n vectors span of V and S equal to W1 to Wm m vectors be linearly independent set of vector in V. And then we have to show that m less than or equal to n. And the given term is two term. S is the n vectors, set of vectors n vectors span of V and again S equal to m vectors W1 to Wm set of vectors be linearly independent set of vectors. This W1 to Wm is linearly independent set of vectors. This S is the span of V. Then we have to show that m less than or equal to n. Let us see the proof of the theorem. Since that term S is span of V, so L of S equal to V. Every vector in V and in particular W1 is the linear combination of that V1 to Vn and V1 to Vn. Here first element W1 is the linear combination of that vectors. Hence S1 equal to inserting that W1 and that set is linearly dependent set of vectors. Inserting the element W1, therefore hence S1 equal to W1, V1, V2, etc. Vn is a linearly dependent set of vectors. Here W1 is the linear combination of that term, so it is dependent set of vectors. Hence there exists a vector Vk not equal to W1. In S1 which is a linear combination of Vk is the linear combination of the preceding vector. So deleting that Vk, Therefore, let S2 equal to W1, B1, B2, etc. Bk minus 1, deleting Bk, therefore Bk plus 1, etc. Bn. Clearly, that's it. Here Bk is the linear combination of the preceding vector, so Vk is the deleting term. V1, W1 is inserting. Clearly, L of S2 equal to V. The L of S2 equal to the whole linear span. Hence, W2 is the another vector. W2 is the linear combination in S2. W2 is the linear combination in S2. Hence, S3 equal to inserting that element W2, comma W1, V1, Vk minus 1, Vk plus 1, etc. Vn is linearly dependent. Hence, there exists a vector in S3. S3. Here, there exists a vector in Vj is the linear combination of the preceding vectors. Vj is the linear combination of the preceding vector. Since Wi's are linearly independent, this vector cannot be W2 or W1. Hence, must sum Vj's j not equal to k with j greater than k. Deleting of Vj's from S3 and inserting the vector W2, deleting Vj from the set S3, it gives S4. S3 gives the set S4 equal to W2, W1, V1, Vk minus 1, Vk plus 1, deleting the vector Vj. So, Vj minus 1, Vj plus 1, deleting the vector Vj. Vj is the linear combination of the preceding vector. That term is deleting. So, Vj minus 1, Vj plus 1, comma, etc. Bn of n vectors spanning B. In this process, at each step, we insert one vector from W1, W2, Wm and delete one vector from V1, V2, etc. Vn. If m greater than n, after repeating this process n times, we arrive at the set of vectors Wn, Wn minus 1, etc. W1 which spans B. Therefore, Wn plus 1 is the linear combination of W1 to Wn. Therefore, this is linearly dependent. If m greater than n, here m greater than n, this process n times, repeating this process n times, we arrive the set which spans V. Therefore, Wn plus 1 is the linear combination of that term. Therefore, W1, W2, etc. Wn plus 1, Wm is a linearly dependent, which is contradiction. Hence, m less than or equal to n. Hence, the result. Let us see the another theorem. Any two bases of finite dimensional vector space B have the same number of elements. Two bases of finite dimensional vector space have the same number of elements. Number of elements are same. You have to show that number of elements are same. Let us see the proof of the theorem. Since B is a finite dimensional, it has two bases. One is S, another one is S dash. S equal to n vectors V1 to Vn and S dash equal to W1 to Wm. Another basis for V. But L of S equal to V, L of S equal to V, this set of vector is linearly independent. Hence, the above theorem, we use them m less than or equal to n. Here, S dash is set of m linearly independent vector. M linearly independent vector. The above, using the above theorem, m linearly independent vector. Therefore, m list of that m less than or equal to n. Also, L of S dash equal to V. Here L of S equal to V and S dash is the set of m linearly independent vectors. Hence, that linearly independent set of vector is the smallest. Therefore, using the above theorem, m less than or equal to n. Also, L of S dash equal to V. L of S dash equal to V and S is the set of m linearly independent set of vectors. S is the set of n linearly independent vectors. S is the linearly set of n linearly independent set of vectors, so least value is n, and therefore n less than or equal to m. Here m less than or equal to n and n less than or equal to m, hence from these two terms, hence m equal to n, hence the number of elements are same, hence the result. Thank you.